Hello everyone, welcome to this presentation entitled Introduction to Variable Inductors. This is the second part of this presentation. First, in part 1, we saw an introduction to variable inductors, and we also explained how to do the analytical modeling of variable inductors. Now in this second part we are going to show how to do the spice-based modeling of variable inductors, and then we will see several examples of applications of this type of magnetic devices. Finally, we will see some conclusions. Remember that this is an excerpt of my book entitled Inductors, Variable and Controllable. So if you are interested in this topic, please take a look at the content of this book. And also there are two other videos in this channel related to this topic, which are Power Electronics number 5, Spice Modeling of Magnetic Devices, and Power Electronics number 13, DC Inductors under nonlinear operation. So the modeling of variable inductors and magnetic devices in general is important because we can have a knowledge of the behavior of the device previous to its manufacturing in the laboratory. Also, we can get a better understanding of these complex magnetic structures, and usually we can find two typical modeling methods. One is the use of finite element analysis, FEA. This is interesting because it can provide a high accuracy, but the problem is that it's quite time consuming and it is difficult to interact with other simulators in order to allow for complete simulation of the power converter and the magnetic device. So spice-based models are much quicker to implement and also to simulate, and we can integrate these type of models into our electrical circuit and do the complete simulation in a spice-based simulator. So let's see how to do this spice modeling of variable inductors. As we have seen in part 1 of this presentation, our variable inductor can be modeled using the equivalent reluctance circuit. So we have the different reluctances, the reluctance of the core here, the reluctances of the air gaps, and then we have the magnetomotive forces and so on. So we need several elements in order to do the modeling of our magnetic device. We need, for example, constant reluctance elements to implement the air gaps and maybe other non-magnetic materials in our structure. But we also need what we call variable reluctance elements. These are these elements here, in which the reluctance depends on the permeability of the material. And finally, in our structure, we have also windings, so we need to also model the behavior of the winding, in which we have the interaction between the magnetic field of the structure and the electrical field of the device. So now we are going to see how to model in SPICE these different elements. First, the constant reluctance element to model the air gap. This element is very easy to implement because it is going to behave just as a resistance in our electrical circuit. So this is equivalent to the Ohm law. We have the current, which is the magnetic flux in the core. Then we have the reluctance of the air gap, the constant reluctance, and then we have an equivalent voltage, which is the magnetomotive force, which is equal to the magnetic flux times the reluctance. And as we know, the equation for obtaining the value of the reluctance of an air gap is given by this expression here, where L0 is the length of the air gap, mu0 is the permeability of the free space, A0 is the cross-sectional area in which we have the air gap, and finally we add here this factor, which is the fringing factor, to allow for the fringing effect. So usually in the ideal conditions this factor will be equal to 1, but if we want to consider the fringing of the magnetic flux, then this factor can be a little bit higher than 1. Next, we have the variable reluctance element, and this element is to model a piece of magnetic material with a given permeability mu, but taking into account that this permeability is going to depend on the magnetic flux density that we have in the core. So the magnetic flux density is B here. So we are going to model this element also by using a resistance here, which is the ratio between the magnetic flux and also the magnetomotive force across the element, as we have seen before. And also the value of the reluctance is given by the length divided by the permeability and the cross-sectional area of the material. However, now we have to consider that the permeability mu is going to depend on the magnetic flux density, so we need to model the BH curve of the material. Here in this figure we can see the typical characteristic BH of the magnetic material. So in order to do the modeling of this curve, we are going to use the Brouwer's model, which is given by this expression here. This is a very nice expression, very easy to use. So from this expression we can get the permeability as the ratio between B and H, and it is given by this expression here. And as we can see, it is going to be a function of the magnetic flux density. So what we need now is to obtain the parameters K1, K2 and K3 from the datasheet of the manufacturer. Here we have an example of how to obtain this information from the manufacturer datasheet. We have here the characteristic as shown in the datasheet for the material N87. So from this information we can get the different values of the magnetic flux density and the magnetic field intensity. Here we can see this graphic representing the magnetic field intensity and versus the magnetic flux density. In red we have the different points corresponding to the values from the data sheet, and in green we have the Brouwer's approximation. So this is the equation corresponding to the Brouwer's formula. From it, using some mathematical software like WinPython, we can easily obtain K1, K2 and K3, and then we can use these values for the equation of the magnetic permeability of the material. With this we have everything, and then we can implement our variable reluctance element. Here we are using this behavioral voltage source EM in order to emulate the equivalent resistance corresponding to the reluctance. And the value of this voltage is given by this expression here, which is the value of the reluctance, is the length divided by the value of the permeability and the cross-sectional area, and then we multiply by the current which is circulating through it to implement the resistance. And in order to generate here this value corresponding to the permeability, we employed these other two elements here. With this circuit here, we calculate the value of the magnetic flux density, just dividing the current through our reluctance by the cross-sectional area. So the voltage here is going to be the magnetic flux density, and then using this value here, we use this other current source to generate a voltage that is going to be equal to the value of the magnetic permeability. So we employ here this expression, which is mu, as a function of the voltage corresponding to the magnetic flux density. And finally, we include a directive like this in order to define the function mu. Finally, we have the modeling of the winding. In the winding, we have the interaction between the magnetic field and the electrical field. So we have these simple expressions. We have that the voltage across the winding is going to be the number of turns times the derivative in time of the magnetic flux. And then we can express the magnetic flux as the area times the magnetic flux density. So we get this expression here. And then we also know that the magnetomotive force is equal to the number of turns times the current circulating through the winding. So with this we have all the information, and then we only need to implement this behavior in SPICE. This is the implementation of the windings in SPICE. Here we have two parts. We have the electric part of the winding and the magnetic part of the winding here on the left. So both of them are related. Here in the magnetic part, what we are implementing is this expression here, the magnetomotive force, which is the number of turns times the current circulating through the winding. So we implement this using this behavioral voltage source with a value equal to the number of turns times the current, which is circulating here through the winding. And then in the electrical part, what we are doing is to implement this differential equation here, the number of terms times the derivative of the flux with respect to time. So we do this derivative using an inductor here, in which the value of the inductance is equal to the number of terms, so is this factor here. And then the current that is going to circulate here through the inductor is going to be equal to the flux that is going through the magnetic part of the structure at which or on which is attached the winding. So with this behavioral current source, we make this current equal to the current that is circulating through the magnetic element, which at the end is the flux that is circulating in the material. Note that we need to add here this series resistance in order to avoid convergence problems. Finally, this is a summary of the four basic components that we need to model the variable inductor in space, the air gap, the linear reluctor, the nonlinear reluctor with the permeability as a function of the magnetic flux density, and the winding. These elements are available from my website here, and also these and other elements are also explained, as we have said before, in this other video, Power Electronics number 5, with more information about SPICE modeling of magnetic devices. This is an example of modeling the variable inductor that we have seen before in SPICE. Here we have the different values of this variable inductor. This is the core that we are using, an EFD25 with the dimensions of the lateral arms here and the central arm here in this part. So with this we have all the information to do the SPICE modeling of the device. Here we can see the implementation of the variable inductor. So we can see here the three arms of the variable inductor with the three variable reluctors, the three air gaps, and also the three windings. This is the main winding, and these other two here and here are the auxiliary windings to bias the magnetic flux density inside the structure. This is the main winding here, which is connected here to this voltage source. So with these directives here, we can do the simulation and obtain the value of the inductance at each operating point. To bias the magnetic flux density, we use this current source here, so we can change the current that is circulating through the bias windings, and then we can change the value of the inductance. These are some simulation results compared with the theoretical analysis that we have seen in the first part of this video. So we can see in the blue squares are the results of the simulation, and the blue line is the result of the theoretical analysis. So we can see here is the DC flux density as a function of the DC bias current. We see that they match very well, and here we have the inductance of the main winding as a function of the DC bias current, so we can see also that the matching is very good. This is another simulation, but in this case to obtain the inductance of the bias windings. So in this case we are using this current source with a given DC value and with an AC value superposed to it. And with this, using all these statements here, then we can also calculate the different values of the inductance of the bias winding, the DC inductance, and also the differential inductance, as we have seen in the theoretical analysis in the first part of this video. And this is the comparison between the simulation results and the theoretical analysis. And the solid lines are the theoretical analysis here, corresponding to the DC value of the inductance of the bias windings, and the triangles corresponds to the simulation results. And the effective value of the inductance of the bias windings again is this line here in blue corresponding to the theoretical analysis, and the green squares correspond to the values of the simulation, so we can see that they are also in good agreement. But of course, the most important test is to compare the experimental results with the theoretical or the simulation results. So here we are showing the inductance of the main winding as a function of the DC bias current through the auxiliary windings. So in red we have the experimental results obtained from the prototype at the laboratory, and in blue we can see the curve corresponding to the theoretical analysis. So we can see that the matching is quite good, taking into account the complexity of these magnetic devices. So in this last part of the presentation, we are going to see some examples of applications in which variable inductors can be used. Variable inductors can be used, for example, in the control of resonant inverters. We have used variable inductors in the control of resonant inverters in applications to supply discharge lamps like fluorescent lamps. So we can include here in our resonant tank a variable inductor. So if we calculate the power that we are going to supply to the lamp, is going to be an expression like this, in which we have a parameter which is the inductance. So if we change the value of the inductance, then we can change the value of the power in the lamp as a function of the inductance, and then we can have these different curves for different operating frequencies, and this allows us to implement different strategies to control the lamp power. Variable inductors can also be used in the control of resonant inverters to the implementation of DC-DC converters. So here we have our resonant inverter, in which we are including the variable inductor here in the resonant tank. So the equivalent circuit is going to be like this. If we represent the DC output voltage of the converter as a function of the inductance, then we have these different characteristics. So we can change the value, or we can regulate even the DC output voltage while keeping the switching frequency of the converter constant. So in this way, as we can see here, we are measuring the output voltage, sending this information to an error amplifier, and then acting on the variable inductor to do the regulation of the output voltage in closed loop. This is another example of application. This is a single inductor LED driver in which we have an inductor, a transformer, and then we are supplying the LED lamp. So if we analyze this type of converters, we are going to have a current circulating through the inductor, which is something like this triangular waveform. We rectify this current, and then we inject the current into the output, into the LED lamp. So the average current is going to be something like this. This is the rectified current, and this is the average value. If we analyze this converter, then we will see that the average current that we are injecting into the lamp, it depends on the value of the inductance, so we can control this value of the current by changing the value of the inductance. Another example of using variable inductors is to control DC-DC converters operating in discontinuous conduction mode. So if we represent the voltage ratio of our DC-DC converter as a function of the inductance, then we can obtain characteristics like this. So it is possible to regulate the output voltage by adjusting the value of the inductance. So here we are showing the buck converter, in which we are measuring the output voltage, sending the information to a compensator, and then controlling the current that is circulating through the bias windings of the variable inductor. Then we can regulate and control the output voltage. For more information about this particular topic, you can take a look at this video, Power Electronics number 25, Magnetic Control of Hard Switching DC-DC Converters. So, as conclusions of this presentation, we can say that variable inductors can be used to provide additional control parameters in power electronics converters. Also, the analytical modeling that we have seen in this video is very useful for designing and evaluating these magnetic devices. Also, the spice-based modeling that we have seen in this presentation is very useful because we can do the complete simulation of the converter, including the variable inductor model. And we can say that variable inductors have been successfully used in many different power electronics applications, and also that new ideas and applications are expected to come in the future, because there are many possibilities of using this type of devices in power electronics converters. Well, this is all in this presentation. Thank you very much for watching. Please let me know if you have any comment or question, and I hope to see you in the next video. Goodbye now.